Good evening, folks. Welcome to our first Nuclear Masterclass webinar. It's great to see so many of you joining us live. I'm Dr. James Cubiss. I'm one of the researchers at the University of York who specializes in nuclear structure physics. So before we start, I've got a couple of housekeeping bits to do. Just a reminder to everyone that this session is being recorded. If you would like subtitles, you can turn those on by using the CC or Show Captions button that you should find at the bottom of your screen. If you have any Wi-Fi issues, you can rejoin the session at any time using the same link that you used to join already this evening. And just to know that the recorded session will be shared with all ticket holders and on the Nuclear Masterclass webpage early next week. So we're going to have two speakers this evening, which is great, and hopefully with time at the end we'll have a Q&A session. Just to say to put all your questions into the Q&A session at the bottom of the screen. You can post those questions throughout the presentations. No need to wait till the end. We'll be collecting them as and when we can, and I'll put as many of them as I can towards the speakers. So this evening's session, we're going to have a really nice, interesting talk, finding out about nucleus shapes and delving into a particularly special nucleus state known as the Hoyle state. So we've got two speakers. We've got Kokalova Wheldon, who's a lecturer and a researcher in nuclear physics at the University of Birmingham, and her research focuses on exotic nuclear and nuclear astrophysics. She's a director of the University of Birmingham's Positron Image Center, and she was named in the 2020 TimeWise Power 50 Awards, a roll call of 50 powerful executives in the UK who also work part-time or flexibly. We've also got Dr. Stuart Pirrie, who is a lecturer at the University of Birmingham also, and his research focuses on experimental low-energy physics and molecular physics. So without further ado, I'll hand over to Tzany to begin the talks.
It's lovely to be here tonight. So you can see I'm in my office. You can see also something you'll also see in my slides in a minute. Stuart, I think that you have switched on your camera. If you want to put your sound as well, we can probably also see you.
Hello, everybody.
Excellent. So I will then take it away, James, and start with the presentation, since I'm sure everybody are eagerly awaiting to hear something more about the nuclear world. What we're going to do now is we're going to spend about 30 to 40 minutes together with myself. You'll spend together with myself and Stuart, Dr. Stuart Pirrie, and we will take you into the amazing world of nuclei. So you'll hear about the Hoyle state, and you'll hear also about something called nuclear molecules. So let me start first by simply introducing to you something you're probably well aware of, or you have seen many times in chemistry or throughout your study. So this is the very well-known periodic table of elements, and exactly the same way you have here the elements organized by the number of protons and their properties, we have something similar in nuclear physics, which is called the Segre chart. This chart was proposed by Émile Segre, which is a French physicist, and it's a chart of nuclides. So what we have here is, you can see on the x-axis, we have put the number of neutrons, and on the y-axis, you have the number of protons. So now when you look at that table, what you can see there is it's all very much zoomed out, because we have over 3,500 different nuclei, different isotopes nuclei, where you have different numbers, the same number of protons, but different numbers of neutrons, and also different nuclei altogether. And the 3,500 is about the number of nuclei we have managed so far to reproduce to some extent in the laboratory, so that we could study or observe them enough so that we know they exist. Theoretically, on the basis of our understanding of the nuclear force and what we currently have in terms of nuclear models, we have predicted more than 7,000 different nuclei to exist. So you can see that we have been able to reproduce in the laboratory only about half of those. Interesting fact here is that only about 300 of the nuclei are stable, But what I have done here for you is I've gone even one step further when I've been plotting for you this graph with different nuclei. I have not looked into the standard way. You will see this table, and actually the way the table looks behind me, which is when you look at how the different ways of decay nuclei have. I have actually plotted here for you the nuclei looking into their shape, because this is something which is normally slightly overlooked when we talk about nuclei, especially at schools. And in fact, nuclei have diverse shapes and very exotic shapes, something which is really definitely not only to be mentioned, but also to be celebrated. So what I have done here is, if you look at the colors, you will see that there are all sorts of different colors. You have nice yellows, greens, blues, and etc., but they all relate to some form of the nucleus, and in this case, how deformed the nucleus is. And I'm saying deformed because normally the picture you're given at school is that nuclei is spherical, a sphere which is full of nucleons, protons, and neutrons, kind of like almost homogeneously distributed. But in fact, majority of nuclei are not spherical at all. Majority of nuclei are more like a rugby shape, or what we call prolate deformed, but actually really does look like a rugby ball. And you also have another quite interesting, sometimes tasteful shape, which is like M&Ms. This is what we call oblate deformed. And if you look at this, as I said, majority of nuclei, all this part here where we're talking about quite deformed nuclei, more than 70%, those will be predominantly prolate, with some small percentage also oblate or M&Ms. Majority of rugby balls, some are like M&Ms. And those which you can see here, where you see the crossings on the lines, which are more purplish, they're almost spherical. With one really good example here of spherical, this purple right at the beginning, which is the alpha nucleus, which is the helium-4, where you have 2 protons and 2 neutrons. And this is very special, and we will talk about this throughout today, because we will be talking about also this rise to exotic shape in nuclei, where you have deformed them so far that they might already or have already pre-built alpha particles, or look like they're made out of alpha particles. Now, if that has not blown you away, what really should blow you away is the fact that if we look at the lead nucleus, so one of the lead isotopes only, just one nucleus, if we look there, not only you can have these vast shapes, and you have those vast shapes, different shapes and exotic shapes throughout the Segret chart, but also within one nucleus. And I have put here for you lead 186. So this is an isotope of lead which has 186 nucleons. This is the total numbers of protons and neutrons together. If you give energy to the nucleons, those 186 nucleons, they start rearranging themselves and can make shapes, different shapes, even within one nucleus. And this is what here is plotted. Ignore the kind of like the formulas on the side. What you have here is a nice surface which tell you how much energy you have given to your system. And you can see here, if we don't give any energy to the lead nucleus, in what we call ground state, where you don't have any energy, you have not given any energy, those 186 nucleons actually arrange themselves in a kind of like ball shape form, spherical form. But if you give them a little bit of energy, and this is actually not very much on the scale of things, it goes like M&M. And then if you continue giving energy, what you can see is that actually goes even prolate deformed, or it takes the shape of a rugby ball. And that's just a small example, really, of just touching about all the different shapes and possibilities there. Now, how those elements have been made, all those different shapes and all those different isotopes, that has been made so the I mean, we have asked ourselves this probably from the origin of understanding, in terms of the first Homo sapiens probably looked at the stars and wondered how everything around us is made, not just the stars. And in fact, in the 50s, that was really a very subject which was very intensively researched. And something very famous here I would like to point out to you is this famous B2FH paper, which was the pinnacle in understanding of how elements have been made in 1957, quite many years ago, by Burbage, Fowler, and Hoyle, who actually suggested in this paper how elements have been made, how elements have been forged in the stars. And why we're talking about elements being forged in the stars is because something you know from school, and actually right from the beginning you start school in reception, you're given this concept of being Big Bang and the Big Bang theory. But what happens is that after the Big Bang, you actually have very few nuclei which are there. And this is what we call primordial nucleosynthesis. So those are just here in, we're talking about protons, probably some deuterium, which is a proton and a neutron, system of proton and a neutron together, probably some alphas, but hardly a very, very small amount, predominantly just protons. Now, the question which was still there after this famous paper and this explanation about how you can make and the primordial nucleosynthesis and nucleosynthesis in terms of synthesis of elements in stars was that we could not explain, our colleagues could not explain why on earth there is so much carbon and oxygen in the universe, why they're so abundant. And we know this is vital for us as humans, since we are carbon-based life, and for everything around us to be the way it is. So if you look at this graph here, which I've put for you there, is just to show you what was there and how you kind of like get stuck. You know, you can produce a little bit of carbon and a little bit of oxygen, but not in those vast majority. This amount we have observed, and not only is really vital for the existence of life. So this was. Now, if we look at this explanation, look at this sun, immediately your screen brightens up. No, all this energy, you can almost feel it. We understand very well, and that was really well explained in the Burbage, Fowler, and Hoyle paper, that in stars which follow the main sequence, like our sun, what happens is you're fusing together those protons. You can see here we're fusing 4 protons. Those red dots are the protons. You fuse protons, you're burning hydrogen fuel in the sun. This is what really gives rise to those temperatures and light luminosity. And actually from 4 protons, after a significant amount of time, you can make an alpha particle. And we are somewhere around halfway through the life of the sun. And you can imagine that in another 5 or so billion years, all of this hydrogen the sun has will be exhausted. And then you will be left with a lot of alpha particles. And that was where the problem was. What's going to happen, or what happens after you have made all of those protons? You have kind of like fused them together in those vast temperatures and densities into alpha particles. And you'll say, well, very easy. We're just going to fuse now the alpha particles and continue forward. Yes, but no, because once you fuse 2 alpha particles together, and I made a little cartoon for you, a little video, you make something which is called beryllium-8. This is a nucleus which is made out of 2 alpha particles and now has 4 protons and 4 neutrons. Now that form, this nucleus, is very, very short-lived. So that structure exists only for 10 to the minus 16 seconds. And what needs to happen in that very short period of time is another alpha particle needs to join them. And that was what Sir Fred Hoyle predicted, a Yorkshire physicist. And this was the Hoyle genius, because he said, we exist, life exists. So for nucleosynthesis to continue, to proceed further and to have so much carbon and oxygen in the universe, there must be one of those states, which I showed you like in lead, some organization of the protons and the neutrons when you have given energy to the system, to the nucleus, which actually is made out of 3 alpha particles. And not only that, but this structure also can get rid of the energy or a big part of the energy it has. And this is this squiggly line, which is like a photon of energy, so that it can go down, relax into a very stable, comfortable state, which is carbon-12, the stable nucleus. That excited structure, so this 3 alpha structure, which Hoyle predicted must exist, also is extremely short-lived. Again, this 10 to the minus 16 seconds. Phenomenal. Absolutely crazy, but that was this prediction or this idea he had, that this exotic nuclear structure must exist at specifically that energy, made almost 8 orders of magnitude difference in the production of carbon in stars. This is why this is the only structure, the only state in nuclear physics which has its own name, and it's called after Hoyle, the Yorkshire physicist who predicted it. So this is the famous Hoyle state. Now, this was really the missing piece in the jigsaw of understanding how nucleosynthesis can continue and actually build heavier elements in the stars. Now, you might say, okay, this is really already very interesting, but where is all this leading to? And it led to a lot of wonderful discoveries when we talk about those clustered nuclei. So states, structures in those nuclei, when you give, and this is throughout the Segret chart, when you give them energy, that you preform those alpha particles within the nucleus, and then you can have those interesting clustered formations, clusters of alphas together. Now let's look at this beryllium-8 and the carbon-12, which I just showed you, made out of alpha particles. We said those live 10 to the minus 16 seconds only. Very fast. You'll say kind of like a blink of an eye. And actually much, much faster than even that, because 10 to the minus 16 is to 1 second what 1 second is to 300 million years. Just take a bit of time to really get your head around this in terms of putting really orders of magnitude in perception, in perspective. So now what is really interesting here is that if we take this very, 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 very unstable structure, which falls apart immediately into 2 alpha particles, if we just put 1 neutron to the 2 alphas, and actually make now beryllium-9, or we add, as you can see here, this blue circle, this blue dot, which represents the neutron pictorially. So if we add this to the carbon unstable structure, those structures live more than 13 billion years. They're stable, but how, you know? So this is phenomenal. And that also tells you that there must be something special behind this. There is some manifesto of the strong force there, something which really drives this total instability to such a strong stability. And here I will stop for a little bit, and I will give the word to Stuart Pirrie, Dr. Stuart Pirrie, who during his time here at the University of Birmingham with me, did his PhD studying exactly these nuclear molecules, those unstable alpha clusters, which somehow, almost like by magic, are bound by those neutrons when you add them.
Right, thank you, Tzany.
The floor is yours.
Okay, so carrying on from what Professor Kokalova Wheldon just said. So we're looking at beryllium-9 versus beryllium-8. So beryllium-8 lives for a very, very short amount of time. And beryllium-9 lives for a much longer amount of time, so billions of years. So it's what we would consider to be stable. So what I've got plotted here, so here we've got a kind of visual representation. So beryllium-9 is 4 protons, which are the red balls here, and 5 neutrons, which are the blue balls. And what we've got here is that this is something called cluster shell model calculations. Don't worry about what that means necessarily, but these are theoretical predictions about where these particles should exist. And so because beryllium-9, we know looks like in some way two alpha particles, so two helium-4 nuclei, two protons, two neutrons, bound together in some way by some neutron, we can basically plot the way that the alpha particles are positioned versus how the neutron is positioned. So here on the bottom, we have a sort of a heat map, basically, of where we predict the alphas should be at any given time. You can see they form a nice kind of dumbbell shape. So the alphas are sitting here quite calmly. But what's quite interesting is what the neutron is doing. So the neutron, it turns out, acts a lot like electrons do in chemical molecules. So in chemical molecules, we have electrons that get shared between atoms, and these electrons bind together the two atoms by the electrostatic force. So the neutron does the same thing here, but it combines the two alpha particles together by the nuclear strong force, which is pretty crazy. And actually, if we put different levels of excitation energy into the nucleus, we see different ways that the neutron can bind the two alphas together. So in this case, on the right-hand side here, we have sigma bonding. You see the neutron spends most of its time in the middle, where the neutron is sort of tunneling through the alpha particles. In the same way that we have in quantum mechanics, you might have come across the phrase quantum tunneling. So this neutron is tunneling through the alpha particles and binding them together via the strong force. And in pi bonding, the neutron is sort of doing an orbit more like this. And this, it turns out, greatly increases the stability of these two alpha particles, because obviously the alpha particles have two protons each, so they have some sort of electrostatic repulsion. The positive charges repel each other, but the neutron overcomes that, and with the strong force, it keeps them all together and stable. So what I'm going to be talking about in more detail is an experiment that we did, so myself and Tzany and a few of our colleagues. So the experiment was done a few years ago. The analysis happened during my PhD, and we were looking at a nucleus called oxygen-18. So oxygen-18 is 8 protons and 10 neutrons. And it turns out there are a lot of predictions theoretically that if you excite oxygen-18, you get these sort of weird shapes. And one of the shapes that are predicted to get is this thing here, this nuclear molecule. So this is carbon-12 and an alpha particle bound together by 2 neutrons. If you count up, so 6 protons, 2 protons, that makes 8 protons, 6 protons, 6 neutrons, 2 neutrons, 2 neutrons, makes 10 neutrons. So that's oxygen-18 there. And we predict, so this structure is predicted, and actually you can see it's predicted at an excitation energy of about 19.35 MeV. An electron volt is 1.6 times 10 to the negative 19 joules. So it sounds like quite a small amount of energy, but in terms of nuclei, that's quite big. And then we have this other structure predicted, which is core plus alpha. So we have an alpha particle orbiting a smaller nucleus. So this carbon-14 and this alpha particle exists as a sort of two nuclei system. So to measure this, we ran an experiment at a place called the Meyer-Leibniz Laboratory, which is a laboratory in Munich. And this is the setup that we used. I'm going to talk about this in detail here. And this is the reaction. And this is the way that we tend to write nuclear reactions out. So lithium-7 here in purple, that is our beam. So we had a beam coming from something called a tandem accelerator. And the beam is fired down at a high energy into our carbon-12 target. So that's our target here. So the lithium-7 smashes into the carbon-12, a nuclear reaction occurs, and we produce some product particles. So the products are given here. So the proton and the oxygen-18 are our product nuclei. So the proton, in red, is measured here by this thing called the Q3D spectrograph. And our oxygen-18, and this asterisk here means it has excitation energy. So it's not in the ground state. It's excited. It can break apart. And what we were trying to actually measure is how it could break apart. Because if these things break apart, so if you bear in mind when we're looking at this structure here, if we had oxygen-18 looking like this or looking like this, we might expect it to alpha decay a lot more than we would predict otherwise, because there's a preformed alpha particle sitting in these structures. So it's obviously quite easy for a nucleus to just get rid of that, shoot it out. And as such, we're able to see potentially a higher amount of alpha decay. And that's the way we were trying to decide whether or not these structures existed. So the first thing I'm going to talk about is the lithium-7 beam. So how did we get this beam? How is it produced? What is a tandem accelerator? So first thing I'm going to say is that we used it to accelerate lithium-7 to 44 MeV. What that is about 7.04 times 10 to the minus 12 joules. And obviously in the macroscopic world, in the world that we live in, joules is a pretty usual unit of energy. I mean, if you took something, a mass of 1 kilogram and dropped it a meter, you would have about a joule of energy. What we find instead, for very, very small things, is if we convert this energy into a temperature, the temperature is this, which I've written out, not in standard form, I've written out as a number to scare you. So you can have a look at that number and be horrified by how big that is. I mean, we can do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it's a little bit, it's well above the temperature of the surface of the sun. It's a little bit under the temperature of the core of the sun, but we're getting there. So it's very, very hot. So the way that we accelerate these nuclei is we do something quite clever. So this here is some sort of tube, which we have a potential difference. So 0 volts here, positive potential difference here. So positive potential. So this is a positive potential difference. And then we have 0 volts on the other side. So this is a negative potential difference going towards the right. And this thing here is called a stripping foil. So what we do is we take a bunch of negative ions and we feed one in to the edge of this tube. So the attractive force, because this is negatively charged, it's attracted to the positive plate here. So it accelerates and gains kinetic energy as it rushes towards this thing here. And now this is the very clever part. So it hits this stripping foil. It's called a stripping foil because when it hits it, electrons get removed. So the electrons are removed from this negative ion, which turns it from a negative ion into a positive ion. And now there's a positive ion. It's having a miserable time at this positive plate. It wants out. It wants to be gone. So it flies off. It's repelled. It goes all the way to the other end. We're able to accelerate it from one end to the other. And we actually end up with something that is stripped, and ideally it will be completely free of electrons at the other end. And this positive ion goes through and it enters our chamber where we can do some interesting physics with it. The next thing we can talk about is this Q3D spectrograph. And this is where we measured our proton. So the proton that comes out after the reaction of the carbon-12 and the lithium-7. So the proton goes through this thing called a quadrupole magnet. And what that does is it basically just focuses the beam. So then it gets bent. So obviously because it's a charged particle, it gets bent by a magnetic field. It has an electric charge, so it is curved in a magnetic field. And we have 3, and this is why it's called a Q3D. It's a quadrupole and 3 dipoles. The dipoles bend the particle round until it lands on this thing called a focal plane detector. And the only thing that you really need to know is that the amount of energy for a given particle, so if we have any protons going in here, the proton's energy determines where on this focal plane it's going to land. So if we have a low energy proton, it gets bent a little bit less. If we have a higher energy one, it gets bent a bit more. And then these things hit the focal plane, and we can look at the position of the detection on the focal plane, and from that we can work out the energy. And in fact, if you plot that, which you can do, you see something like this. This is focal plane position on the x-axis, and this is some sort of energy loss, which is to tell us what kind of particle we have. So different particles lose different amounts of energy through material. So protons lose less energy than deuterons. You can see this is deuteron here, D. So separate out the protons. You can see there are some strong lines here, and these lines correspond to excited levels in the oxygen 18. Because if we excite our oxygen 18 nucleus, which is the other product we make, some of that energy gets used up exciting this thing, so the proton takes less energy as a result through conservation of energy and momentum. And we can gate on that, and we can see that we've definitely got a proton. So then the question is, how do we look at our oxygen 18? And what we do is we use a series of things called silicon detectors. So we call these double-sided silicon strip detectors, so DSSD. So what they do is when a particle hits those, we measure its energy through the energy it deposits in the detector. But another thing that we do, which is very clever, is we segment these detectors. So on the front side here, you can see we've got, and this is why they're called double-sided silicon strip detectors. We have different strips of silicon. So if a particle hits a specific strip, only that strip reads out an energy. So we can actually tell which strip the particle has hit. And if it hits the front side, this red strip lights up. And if it hits the back side, and as it travels through, it hits the front side, and then it also hits the back strip. So from the front strip and the back strip that it hits, we can work out, by looking at the coincidence between them, what specific pixel this particle has gone through. And from that, we have a position, we have an energy, so we can do conservation of energy and momentum. So this is what our DSSD array actually looked like. If you look at, so out of plane angle here is basically Y, if Y is up and down, and X is sort of left and right. So this is what our DSSD array looked like. So they're all kind of on their side, because that's the only way we could fit them into the chamber. And from there, we're able to do some pretty cool reconstructions. And actually, if we look, so these are some, so on the left-hand side, we have experimental data that we took while we were working on this experiment. And on the right-hand side, we have something called simulated data. So these are what we would predict to see. So we did some calculations and we predicted that this is what we would see. So these kind of circles here, these represent different particles. So obviously, if we have something like so if our oxygen 18 breaks up into carbon 14 alpha, then we would expect to be able to measure either the carbon 14 or the alpha or both. Because the alpha particle has a lot less mass than the carbon 14, if we do conservation of momentum and the oxygen 18 splits apart, the carbon 14 should take less energy, should have less velocity than the alpha particle. And as such, the alpha particle can travel a lot further. So all of these things around the outside, these are all alpha particles. And inside here, we have alpha particles as well. But we also, this orange ring here is from carbon 14s. And then this even lighter ring here is from oxygen 17 neutron decay. So we can separate particles like that. But obviously, that's not ideal because we have alpha particles sitting in this region, but they're also sitting underneath the other features. But you can see there's very good agreement between what we think should happen and what we actually measured. So these are the real data. Any physicist will tell you that Monte Carlo data, simulated data, are beautiful because they behave exactly the way that you want them to. I mean, look at that. That's just gorgeous. This could have been horrifying, but luckily it's worked out. So everything's fine. So this is another way that we can use kinematics to work out what kind of particle we've got. So if we look at a specific case, well, we've got our beam. So this is our lithium-7 beam incident on our carbon-12 target. So the the carbon-12 target. So what happens is we produce a proton, which goes to the Q3D spectrograph, and we produce an oxygen-18. And the oxygen-18 splits apart into a carbon-14 and an alpha particle. In this case, we measured the energy of the proton in the Q3D. We measured the energy of the carbon-14 in the DSSD, but we don't measure the energy of the alpha particle. But that's not a problem because we can then work out, without having to measure the carbon-14 and the alpha, we can work out what particles they were. We don't measure their mass, we just measure their energy, but we can still work it out. So if we look at what we call the Q value equation for this reaction, so you might not have come across Q values before, but Q values are basically a measure of how, if you imagine like in chemistry, how exothermic or endothermic a reaction is. So in nuclear physics, when we have initial products, so we have our lithium-7 and our carbon-12, if you add up the masses of these things, they're not the same as the masses of the proton, alpha, and carbon-14. And that's because when this reaction happens, it turns out these things are slightly heavier than these things. So some of the mass gets converted into energy. So using the famous Einstein equation, E equals mc squared, we can convert energy to mass and vice versa. So some of the mass gets converted into energy, and that energy gets split between the final state particles, the ones that are being produced. So they get that as kinetic energy. So we can write out the energy given out is equal to the energy of the carbon-14, this is kinetic energy, plus the kinetic energy of the alpha, plus the kinetic energy of the proton, minus the kinetic energy of the beam, because our target, the carbon-12, has no kinetic energy because it's stationary, it's just sitting still. So we can also say that the momentum of our alpha particle is given by, the energy is given by the momentum squared of the alpha particle divided by 2 times its mass. And that actually makes sense, because if you think about this here, so the momentum is given by mv, so the mass times the velocity. So m squared v squared over 2m becomes mv squared over 2, which is a half mv squared, which is the equation that you'll be familiar with for kinetic energy. So this is just the kinetic energy of the alpha particle related to its momentum. And we can sub that in here. So we replace EA here with this expression, and we rearrange, and we get something like this. And what we've done very cleverly is I've separated out the 1 over MA to put it in front. And the reason I've done that is because this expression here, these are things that we've measured. So E beam minus E carbon-14 minus E proton. We actually measured all of those. So we know the energy of the beam because it comes from the accelerator, 44 MeV. We know the energy of the proton because we measured it in the Q3D. We measured the energy of the carbon-14 in the DSSD. We can work out the momentum of the alpha particle through conservation of momentum. So we look at the different momenta here. So we've measured this, we've measured this, we've measured this. The initial momentum is P beam. So we can do that equals the momenta of these 3. We know these 2, so we can work out from that. The only unknown is this. So we work out the momentum of the alpha particle, plug that in here, and we can plot this. And actually this might not be obvious, but this is actually in the form y equals mx plus c. This is just a straight line graph, where our x is the momentum we worked out for the alpha particle squared over 2. Y is the things that we measured. And then we have if we plot these two against each other, y against x, we should get a straight line with a gradient of 1 over m, which is the mass of the particle that's missing, and a y-intercept of the q value, or minus the q value. And what we see is this thing here. So this is called a Catania plot. And you can see there are some very obvious features. So we have this red line here, what I'm showing. So we've calculated this assuming that we've got an alpha particle that's missing. But obviously we could be wrong about that. And actually in the case where we had, instead of having an alpha particle and carbon-14 coming out of our oxygen 18, we had an oxygen 17 and a neutron, they actually sit over here in this region. But the straight line, where we have a gradient of 1 over 4, because the mass of an alpha particle is 4, in terms of protons and neutrons, and the Q value is 173, sorry, which I've told you here. We can see that these events just lie nicely on this straight line. So we can actually draw gates around these things and say, okay, so anything in here was carbon-14 alpha, anything here was carbon-14 alpha, anything here was oxygen 17 neutron. And from that, we can then look at all the things that we measured, and we can work out how much this thing alpha decayed versus how much it's neutron decayed. And if alpha decayed more than we thought, then we can determine whether or not these states are clustered. And this is the sort of thing you see here. So this is my last slide. Well, we can see, so this is the total excitation spectrum. So these are what the energy levels in oxygen 18 look like. So this is if we excite it, we get these obvious states here. If we gate on the alpha channel, so if we look at the carbon-14 alpha events, we can see that some of the states basically disappear. So this 10.587 state disappears. This big state here is very, very diminished. And then if we look at the neutron channel, those states that disappeared, they're very obviously there. So these states heavily neutron decay and don't alpha decay very much. But then we have states like this one here, which heavily alpha decay, because we can see it here, and does not heavily neutron decay. And that's true on this side as well. So we're trying to find states that are heavily alpha decay, and from that we can therefore infer that these things might have a tendency towards being clustered. And that's what we did. So we did this measurement. There was a lot of theoretical interest. We found a couple of states that seemed quite clustered, but we found a lot of states that weren't, and that probably upset some people. But unfortunately, they're crying while I got my PhD. So a win's a win. You've got to take what you can get. So with that, I'm going to pass back over to Professor Kokalova Wheldon.
Well, what a great ending there, Stuart. Fantastic. Yeah, some people are crying, but you got your PhD. Absolutely. So what I can see here now is, and I will just briefly touch on that because Stuart already showed you quite nicely how we can accelerate particles, but how do we study nuclei? What we did for Stuart's experiment, Dr. Pirrie's experiment, and also other experiments is we do something similar to what you know from probably the Large Hadron Collider in particle physics. We do similar experiments, but at a smaller scale, so low energy beams. So what we do in the laboratories reverse of what happens in stars. So here we have a beam of those alpha particles, which are fast moving, coming out of one of those accelerators, which have accelerated them. And then we are accelerating them towards a target. So we're letting them really collide with the target, bash together, and we see what happens when they bash together. We collect all of the parts coming out from there. And this is what really gives us the opportunity, as Stuart showed you quite nicely, taking those alpha particles, collecting all of the bits and pieces after the collision to actually build those so-called spectra or spectrum in this case. And I would like to show you here this spectrum because this is specifically the spectrum for the Hoyle state. And what I will do on the next slide is I will actually let my colleague, Jim Al-Khalili, who I'm sure some of you know very well, who is a very dear friend of mine as well, to show you something he came to Birmingham and we did here, which afterwards was also on the BBC and explained a little bit more about this magical Hoyle state. Enjoy.
In the 1950s, Hoyle joined the California Institute of Technology, Caltech, who had one of the few particle accelerators in existence at the time, similar to this one. Hoyle wanted to use the accelerator to try and make his high-energy carbon. They were not so keen. Hoyle kept at them. Finally, they gave in. The search was on. Today, I'm recreating their experiment. The plan was to bombard a target element with a particle beam to see if they could create that state of carbon. Well, I have with me my own experimental colleagues, Tzany and Robin, to help me out. Our target will be held in the center of this reaction chamber. Now, what they were looking for was a very specific signal that would show up in their detectors. If that state of carbon existed, then Hoyle predicted that it would show up as a spike in the energy at 7.7 million electron volts, the fingerprint of this special state of carbon. We'll be looking for the same spike in energy. Time to seal the chamber, close the radiation doors, and see for ourselves what happened. Right, this is the control panel, and they've let me in, a theorist, to get it all running. So the first thing I do is fire up the beam, then to aim the beam at the target. Charged particles are now slamming into the target. Now, data will start coming in, and the important display to look at is over here. Now, if Hoyle was right, they'd see his excited state of carbon at this energy here. They would expect to see a spike in energy at that point. And there it is. Exactly where Hoyle predicted. He was also right about the fame. The director of the laboratory went on to receive the Nobel Prize for the discovery.
But sadly enough, Hoyle didn't. And there is a lot of stuff you can read about him because he was really a character. So you saw the cyclotron, which we have here at the University of Birmingham, but I would like also to show you something else and use only a couple of minutes to give you an idea about other very cool things we do as a result of nuclear physics and our nuclear physics study, applying what we otherwise use for the research, for the fundamental research in really everyday's life and helping people. So we have, you can see here on this slide, on the 7th of December, so it's really fresh, very fresh. On the 7th of December, we had the first beams of neutrons, which we have now as another accelerator, so proton-driven neutron accelerator, which was commissioned in December at the University of Birmingham. So that what you can see here is part of this proton machine. So this long gray structure is the proton machine, which actually is very high intensity, delivering very high intensity protons, smashing them on this metal. So this, what you have there, this metal part, it encases inside a target which has lithium, and when those protons smash on the lithium, they produce a lot of neutrons coming out, and this is actually what delivers the neutron beam, and it gives us the opportunity to study other processes happening not just in stars, but also to look into fusion, nuclear fusion, fission, and other things which are also very interesting and important. So another little thing, and this is what we do here, and this is also part of what I do as director of the Positron Imaging Center, is we also look into new isotopes for medical treatment. Specifically here, we are talking about cancer treatment, and I wanted to mention to you something which is very exciting. It's the cutting edge of this research development in this area. We're talking about theranostic elements. So those are the same chemical element, but you use different nuclei, different isotopes, which means that from a chemical point of view and how things are metabolized in the body, you have the same element, but actually having a different number of neutrons gives you the opportunity to use for the imaging part, when you use like PET scanners imaging, the same element, and also using this afterwards for the radiotherapy. So this is extremely interesting and really strongly developing, intensively developing part in radiotherapy at the moment, nuclear medicine at the moment, and this is theranostics. So that's something which I did with another PhD student, where we looked into terbium isotopes, which are very promising candidate for that. And this is just to remind you, when I mentioned the PET scanner, so positron emission tomography, what we also have done is we've taken from positron emission tomography the element that positron emitting nuclei, which you've heard, some of you probably and hopefully have heard about beta decay, but this is just for us, what is important at the moment, we're just talking of a way the nuclei can decay, which gives you the opportunity to see two of those squiggly lines, which is just photons, quants of energy, just a chunk of energy emitted. And they're emitted in a way that it's really opposite. So they really draw you a line from where the source, where the nucleus is. And this is how you can follow this. And that is what is also happening in part, or kind of like pictorially given in positron emission tomography in PET scanners, and how they really image the tumors or other problems. So what we can also do with this, and we've been doing that here for about 15, 20 years already, is we have used this and further developed it by tracing really more than 1,000 times per second, and really very precisely this particle which has the nucleus, the radioactive nucleus. And that gave us an opportunity to look into a funky stuff like, for example, what's the best way of organizing or to fill your dishwasher? Or what happens when you're roasting coffee beans? You just have to look at where the radioactive particle is, follow it, and this gives you those pictures like you can see here. Those blues is actually the figures under show you simply where the water is squirting depending on how you have put the plates in the dishwasher, and can give you the optimal distribution there. So in all together, and from both of us actually, if I could speak on behalf of pretty much all of my nuclear physics colleagues, the message I want to give you is, you can see that Segret chart. I have plotted here now for you the different, the whole chart. And this gray area is this terra incognita, this unknown area. Those are the isotopes we have predicted from our knowledge should exist, but we still have not been able to produce in the laboratory. And what I want to show you there is that there is a huge amount, there is a lot of work still ahead of us, ahead of you. And if this is something you would like to follow or something you're interested in, there is really a lot of wonderful work you can do. And last but not least, of course, may the strong force, the nuclear force, be with you. Thank you very much.
Thank you very much, Tzany and Stuart. They were great talks, and we now have a huge number of great questions. So I'm going to go through as many as I can in the remaining time. But just a note for anyone who's on the masterclass, the questions will be available on the question forum, and we'll answer them all there. So my first question, because lots of people were interested in this, goes to Stuart. How does the stripper foil work, and what's it made of?
So that's a good question. So Tzany might be able to. So I can't remember what the specific stripper foil at the Q3D is made of, or the tandem Van de Graaff. So obviously you can imagine, I think, if you look at the fact that this thing was positively charged and we were putting negative ions in it, because it's a region of strong positive charge and there are lots of electrons on this ion, those electrons get ripped out of the ion by the positive charge. The fact there's a positive charge there means we're missing electrons. So we rip the electrons off of this ion, put them to try and decrease the amount of positive charge there is in the stripper foil. Obviously, for one ion, that makes not very much difference for a whole foil. But that's basically what happens. We're ripping electrons off of this thing because of the huge amount of positive charge.
Yeah, you can imagine this as a sieve. And when your particles or your atom is coming through that, it really gets stripped off. It's leaving there all of the electrons and continues as just a positive ion.
Yeah, I think it basically just has to be some metal that can hold a positive charge. So I'm not sure there's that much. I'm assuming there's some level of care, but I'm not sure what the rules are for what they pick. But it's just going to be some metal that can be positive, I imagine.
Yeah.
Thanks, guys. How can the nucleus have shapes if they are arranged by discrete subparticles? For instance, what shape can hydrogen-1 be?
So that's a very, very interesting question. And actually, that is still a question. So whoever asked that question is a deep thinker. So proton, so hydrogen, no hydrogen 1 or proton, you would expect will be spherical. So it will be just like a ball, no, like what I showed you there as basketball ball. But in fact, we have, in studies, we have seen that actually it's not. It can be, so in its, what I called you like the ground state, you know, in kind of like has a ball, which is spherical shape, the proton. But what you have to take into account here is that the proton actually consists of quarks. It's not an elementary particle because it has constituents. So it's made out of quarks. And probably some of you are already thinking, yes, we know it's up, up and down quark, which makes the proton. But actually, what is also quite spectacular there is that the mass of the up, and the down, the three quarks, which are making the proton, if you calculate this yourself at home, you will see that the mass of the quarks actually is only just 1% or 2% of the overall mass of the proton if you compare it. So what really happens is that a lot of the mass there comes out of the residual interactions between the quark and the gluons, which is what really also gives rise to the nuclear, to the strong force. So because the proton is made out of quarks, you can even try to imagine it like a jail where your quarks are confined. So they're moving inside, they're not static. So they're moving inside and they're actually trying to get out. So depending on how fast the quarks are moving inside, that can deform the proton. So that can make the proton look more like a peanutty shape thing going into something like this rugby ball I show you, or even depends how fast they are, because they can move as fast as almost the speed of light. It can get even almost like these M&Ms. So there are different shapes there, despite being just one proton.
Yeah, thanks. So there's one question here which I'm going to use the chair's prerogative to answer, which is, does the nuclear shape affect the atomic electron levels? This is my particular area of research, and the answer is absolutely yes. Isotope shift, it's called, and hyperfine structure splitting is due to a coupling of the shape and the moments of the nucleus to the electron levels. So I'm very conscious we're at the end of the time. I'm going to give one more question, which goes to both of you. Stuart, you showed a ridiculously high temperature for your beam if you converted that into Celsius. The question is, why didn't the beam pipe melt? Why didn't your whole experiment that the two of you performed melt?
So a great question. So the way that the beam ideally works, and this is the ideal case, is we bend it with the magnetic fields so it never touches the pipe. So it's always going through the center, and the pipe is under vacuum as well. So there's no conduction through gas or anything like that. It's just the beam's going straight through, doesn't touch the pipe. If you had a beam hitting the pipe, you would heat it up, and that would be bad. And actually, in a lot of cases, and this happens in lots of accelerators, and it definitely happens here at Birmingham in our accelerator, sometimes the beam gets missteered and it hits a magnet, and the magnet melts. Or some element of the magnet melts, and we go, oh, oops, that should not have gone there. So these things they're very, very high energy. We don't really
go ups, we go and repair it.
I go ups. It's not someone else repairs it. I go, whoa, nightmare. But yeah, so if these things were hitting into the beam, they would be heating it up. It's not quite as obvious. So obviously we talk about that. So temperature is a statistical property. So we're talking about a collection of particles having some distribution of energy, and that represents a temperature. So we're kind of, when we talk about particles having an energy, we're being a bit disingenuous. We're sort of simplifying things. But essentially, these particles would be transferring energy to the metal, and that metal would then heat up, which would then cause its temperature to increase. But luckily, because we steer it using magnetic fields and under vacuum, we don't have to worry about that.
But you can see this, James, absolutely. So when we do direct particle irradiation, for example, for producing radioactive tracers for PET or PET, when we're doing this for proton emission particle tracking, if you use a high, because we normally use high current, so we use a lot of beam. So high current means a lot of particles simultaneous on a small area. If you have a really small metal ball or something which we're radiating, it's really small, then very often they will melt. If you don't take care that you nicely cool this by having some microchannels with water or something else which really cools and takes away this heat which comes from the strong current, really, from the particles which hits up on the material.
Yeah.
It's a very good question. It is really a problem.
Yeah, I think Stuart's answer that this accidentally happens. This, science doesn't work perfectly every time. So you got to try again, and not worry about the mistakes necessarily.
And some of the biggest discoveries have been made by accident.
Yeah, definitely. You'll never know what you'll find by steering a beam onto a magnet. Okay, so we've run a minute over time, so unfortunately I'm going to bring it to an end. I think there were 50 questions in the Q&A session, so that is a massive thank you to the audience, not only for your very great use of the reactions in the actual Zoom chat. I hope you carry on that through the rest of the masterclass. That was really fun to see. But keep up firing these. Really, I cannot stress enough how good these questions are. I wish every session I chaired was this interactive. So with that in mind, the recording of this event will be available. The questions that haven't been answered in the Q&A session, they'll be put on the question forum, and you'll be able to see the questions and the responses there. The recording of the event will be available on the Nuclear Masterclass website either later this week or early next week, and a link will also be emailed to all ticket holders. So once again, thank you to the audience, and thank you to our two speakers this evening, and wishing you all a wonderful Wednesday evening. See ya.
It's been a pleasure.
Thanks, everybody.
Bye, guys.
Bye.
Bye.